Welcome to our first lecture of the spring 2015 season. I'm Gina Parenti. I'm the coordinator of lectures. I have the honor of introducing our moderator for the evening, Peter Lawrence. Peter is president and co-founder of Biomimicry New England and a biomimicry specialist. We're going to be saying that word a lot tonight. From 1985 to 2014, Peter was the chairman and founder of the Corporate Design Foundation, whose mission was to improve the quality of life and the effectiveness of organizations through design.
And I will introduce first Sam Steer. And Sam is Director of Learning with Nature, a nonprofit organization devoted to developing an engaging platform for STEM education grounded in the genius of the natural world.
So, good evening. It's wonderful to be here, and I am going to keep things relatively brief because, as I understand it, a panel is really about getting to interact more with you guys. But I'll talk just really briefly about biomimicry, give you a brief introduction about what biomimicry is. I'm very curious whether you already know what it is. So if you've heard of biomimicry and kind of feel like you kind of know what it is, would you mind raising your hand? Okay. And some people have come even though they don't know, which is really great. So at least they'll hopefully get something out of the introduction. Someone I know literally overheard this comment at a dinner party. You know, is biomimicry the new Cirque du Soleil? It's not the new Cirque du Soleil, at least not yet, not that I'm aware of. But it probably could be a very interesting Cirque du Soleil. But let me just give you a flavor of what biomimicry is by talking a little bit about this guy, a gecko. You might be surprised that probably more engineers are studying this creature than biologists today. And the reason is because geckos have this extraordinary ability of climbing over virtually any surface. And the way they do it is quite interesting. Their foot has an enormous surface area at the nanoscopic scale. And the material of their foot literally fuses atomically with the material that they're crawling over. This happens at in small bits of time, and it allows them to crawl over virtually anything and stick to virtually anything, and that adhesion is incredibly strong because of this atomic fusing and because of the enormous surface area of their foot. But counterintuitively, it is also a reversible adhesive, and that's very odd because normally a strong adhesive is not reversible, but with a gecko it is. And people have been studying this and now can actually mimic this property in our own materials so that today people are able to literally scale glass walls using the equivalent of gecko gloves. So that would be an example of biomimicry or innovation inspired by nature. And biomimicry can be a very powerful approach to innovation because it's based on a very accomplished world. Gecko is one example. This is something from your backyard, the Atlantic razor clam, which is very good at burrowing into the sand, as you can see here, or mud or dirt, whatever. If you look at the amount of force that it uses to dig into the dirt, it really should only be able to go into the muck about 2 centimeters. But it's able to go in over 70 centimeters. And it's 10 times more efficient than any of our mechanical diggers for the amount of energy that it uses. And this is how it does it. You can see in A that it extends this foot down into B, and then it literally in C will pull up, and then in D it is squeezing its shell together, and that's forcing the blood flow into its foot and expanding that foot, which serves as an anchor. But the other interesting thing that happens in D is that movement of the shell inwards causes the sand, it agitates the sand on both sides of its body, and essentially it's turning in that thick sand, it's turning it into quicksand, it's infusing it with liquid. So it's preparing the substrate before it digs into it. And that's something that's very unique and that people hadn't thought of doing. A professor at MIT has now created something. Let's see if I can get this thing to play. You can see the RoboClam. that Amos Winter has been working on at MIT. Okay, so what's important about this to notice is that biomimicry, in mimicking something, some functional attribute in the natural world, may not end up looking like the thing in the natural world. This doesn't look like a clam. But what's important is that its mechanical behavior is like the clam. And so that's an important thing to note. We're not talking about biomorphism. We're talking about, in biomimicry, mimicking nature's functions. Another example from the ocean is the humpback whale. It's one of the things that's remarkable about a humpback whale is that this is an animal that's the size of a school bus, and yet its primary food item is something very small. That's it, a krill. And how does an animal so big obtain enough food to support itself? And the way it does it is the same way you or I would do it. They use nets. And the humpback whale's nets are blown with bubbles. And you can see those in the middle picture. And what the humpback whale does is it turns in these very tight circles while exhaling, and those bubbles serve as a net that corrals the krill together. Then the humpback whales come up through the center and get the equivalent of a large size fish. And that's how they sustain themselves. So the next question is that how does a humpback whale, something again the size of a school bus, how does it manage to pirouette like a ballerina? And it turns out it's the funny looking bumps or tubercles on its flipper that allows it to do this. And what that does is it accelerates the flow of water over their flippers, and it delays the separation of that flow, that nice even flow over the flipper. It delays it so that the humpback whale is able to turn in tight radii, in tight circles, essentially keeping a grip on the water during this incredible maneuver, keeping a grip on the water before it stalls out. For centuries, people have been creating airfoils, wings of various types, for various purposes, and the dogma has always been that that leading edge needs to be smooth. Humpback whales have taught us that you can do it a completely different way and you get different properties. This idea of using a bumpy leading edge in order to change the flow dynamics over that wing has resulted in technologies that are now being applied to wind turbines, to computer fans, to industrial fans, and the efficiency improvement is around 20%. And if you talk to anyone in these fields, an efficiency improvement of 1%, 2%, that's worth investing in, that's worth pursuing. 20% is unprecedented. Another example of biomimicry. Biomimicry is applied at lots of different scales. So we've seen the gecko example at the nanoscale. The last example, this is at the level of architecture and urban design. This is an office building in Qatar, and it is able to withstand these high temperatures because, like the barrel cactus that it's modeled after, it is self-shading. It shades itself during the hottest part of the day, during the midday. So that's what biomimicry is. It's learning from nature to improve technology and design, ultimately to create a human way of life that works with and as well as the natural world. And I just wanted to put these quotes up here because biomimicry is something that some of you have heard of in this room, many of you have not, but it's really filtering into the culture all over the place. And it's exciting to see that it's becoming something that is recognized as a very important approach to innovation at all levels. Amory Lovins, I don't know if you know that name, but he's a really interesting person who studies energy. He works at the Rocky Mountain Institute. He's the kind of guy that the president calls up and says, what should our energy policy be? So there is a world of biomimicry happening today at universities, at companies, all around us. Anybody who's interested in improving technology and design very likely will have heard of biomimicry or is using biomimicry exclusively in their pursuit of innovation. The way this is studied is sometimes by looking at the patent database. So what you're looking at here is the number of biomimicry-related patents over time relative to the growth of the patent database over time. And when you compare those, the number of biomimicry-related patents is expanding much faster than the patent database itself. So it's expanding about 35 times, growing 35 times faster than the growth of the patent database overall. So even though in absolute numbers, it's still a minor part, relatively minor part of the patent database overall, it's extremely fast growing as an approach to innovation. This is looking at a similar pattern of biomimicry-related research that's funded by the National Science Foundation over time, and you can see that same sort of explosive J-shaped growth. There are lots and lots of different programs started recently in the last 5 to 10 years at colleges and universities around the country. There's a couple amazing, remarkable ones here just nearby, the Wyss Institute for Biologically Inspired Engineering, which is right at Harvard, for example, and many, many others. So this is, getting more and more becoming sort of a common way of doing education at the post-secondary level. It's difficult, of course, to forecast the future, but there has been some economic projections on the contribution that biomimicry will have to the economy, and so I wanted to show you that, this is something that is going to become more mainstream in the U.S. economy over time as well. Now, I focus on this because I'm particularly interested in K-12 education, and I think that it's a very promising way of bringing education to kids in a way that they will find extremely interesting, exciting, hopeful. So this is a group of students at a science museum in Ohio, for example, and they're comparing wind blade types, the humpback style one that we talked about earlier, to a straight leading edge one. One of the reasons why I find biomimicry so exciting in education is because it's optimistic, it's hopeful, it's solution-oriented. We have been teaching environmental education for about 50 years in this country, and we teach it a little bit more like this, where we show students, we explain all the different issues, but we really don't give them many options for how to deal with that. And increasingly, educators are looking for something that's more optimal, something that inspires and motivates students instead of just makes them despondent. And I think biomimicry can do that. It's a very different way of looking at the natural world. We are used to looking at nature as something beautiful or something like this. This is typical natural history information you would hear about an organism like a ponderosa pine. What biomimicry does is it causes us to start looking at nature as something to learn about, to learning from. And that's the switch. And once that switch happens, it's really hard to go back. You just can't help but look at nature this way. In my experience, teachers really, really do love teaching about biomimicry. They find it extremely helpful for the goals that they have with their students. So I'll let you just read that quote real briefly. I might as well read it out loud. In the classroom, curriculum around biomimicry supplies excellent material for integrated learning and problem-based learning. The solution-centered focus provides hope-filled explorations of environmental sciences, otherwise complicated and troubled conclusions. We piloted an engineering course that was oriented towards biomimicry this fall. And as far as I know, it's the first full course in a high school setting based on biomimicry and engineering. And these are some of the results. You can see that the national average, when you ask students, are you interested in engineering, the national average is usually around 25%, which is there. After this course, about 75% of the students said that they were interested in engineering. So it was a strong indication to us that this biomimicry-oriented approach to teaching something like engineering was really reaching the students. When you look at just female students, The national average is around 14.5% of female students will say they're interested in engineering. At the end of this course, about 72% said that they were interested in engineering. Another one of the things we were interested in is looking at how this affects how students think about sustainability. And we found that 80% of the students, were very interested in sustainability after the course. And I like statistics, but you can't beat the students' own words. So I wanted to just give you a few of their comments in the post-course evaluations. And this is an image that was taken from students in the course. They are doing a chemistry lab where they create cement using car exhaust and seawater in a process that was learned from coral reefs. So that's just one example. Okay. So I'll end right there. And we'll have time to talk about this more, but Mark is up next.
Sam. Thank you, Sam, very much. Our next presenter will be Mark Dorfman. And Mark is a biomimicry chemist with Biomimicry 3.8 and has been doing that for a number of years. But before that, worked in environmental chemistry and a lot with water and toxicology. And I'll ask, he decided finally that he wanted to shift from his work with environmental chemistry, and I'll let him what was the epiphany that made him make that shift? Mark?
Thank you, Peter.
Thank you for being here.
Yeah, so for about 10 years, I was working for an environmental consulting firm, and we were doing case studies of what the chemical industry was doing to reduce the amount of waste that it generates. Because back in the 90s, waste was like the big environmental issue. And so after doing that for 10 years and meeting with chemical industry folks and asking them what they were doing to avoid the creation of waste, I was getting tired of the less than innovative things that they were talking about, and so I was trying to think, okay, well, what's really next? Where is the real innovation there? And I happened to be sitting in my friend's backyard in Seattle on a sunny day, and just looking at the sun reflecting off the leaves, and I was like, that is where the innovation comes from, because every leaf, every green thing you look at in nature is really a chemical manufacturing facility using energy of sunlight, carbon from carbon dioxide in the air, and nutrients it gets from the soil, and making everything that we value from plants, the fibers, the flavors, the fragrances, everything is made from carbon dioxide and water and nutrients, and you don't see green leaves exploding and creating, killing workers and that sort of thing. So it just so happened that at that time, Janine Benyus, who wrote the book called Biomimicry Innovation Inspired by Nature, that book had come out a year before, and I read it, and I just wouldn't leave her alone until 9 years later she hired me. So for the last 8 years, I've been working for what is a consulting firm. So it's just great to be able to work with companies that are trying to solve problems and to look at how nature approaches the same function to pull ideas from nature, as Sam was saying, not using the materials from nature, but using the blueprints and recipes behind those materials. So that's sort of where my presentation starts, so that most people, when they go out into nature, they're either enjoying the beauty or they're thinking, well, what kind of materials could I take from nature and use? And we want to take materials from nature because we see different characteristics and functions that these materials have that are useful for what we'd like to use. But when, these days now when I'm in nature, I look at the same materials, but I look at them as a library of information. And I look to see what kind of information can I get from those materials so we can figure out how can we make materials that not only have the same kind of characteristics and functions, but are in sync with the environment. So, whether you're going out into nature and you're looking at lightweight, strong materials, or materials that give you color and flavors and fragrances, or can insulate and protect us from various environmental issues, temperature, radiation, whether it be nature's different types of fibers and the different kinds of qualities and functions of those fibers. So, if you look at all of the characteristics of these natural materials, and this is only some of them up here, you'll notice that there are many of the same characteristics that we seek in the synthetic materials that we make. But the characteristics and the functions that give man-made materials those characteristics really boils down to chemistry. And it's that same chemistry that makes these materials so unsustainable, causing pollution or causing public health issues. But all of nature's materials that have these great characteristics are also based in chemistry. And that kind of flies in the face of a misconception that we often tend to have, which is that chemicals are a man-made entity that contaminate an otherwise chemical-free natural world. But nothing can be further from the truth, because nature is alive with chemistry. I gave a presentation one time and I called it "Nature is Alive with Chemistry," and it was in this place that the presentations were going to be in this old theater, so they put the name of the presentation on the marquee. So it said, "Nature is alive with chemistry," and I was just wondering what people thought when they drove by. Is it some 1950s horror movie? But anyway, every organism, doing its metabolism and making stuff, it all boils down to chemistry. So whether it's organisms that live in the land, the water, the air, whether they flower or fly, whether they swim or slither, whether they're just single-celled organisms. And we may think that single-celled organisms are really simple, but especially when it comes to chemistry, it's at the single-cell level that incredible chemical management is going on. It's where chemicals are produced, it's where chemicals are managed, it's where they're recycled. So there's so much to get from just individual cells. But even, the most advanced multicellular organisms are also alive with chemistry. And so nature's been doing this chemistry for 3.8 billion years. And out of necessity, nature has had to figure out how to do chemistry in a way that's life-friendly, because unlike us, you can't be doing chemistry in Texas or Louisiana and then ship the stuff to where you are. Organisms have to do their chemistry in the same place where their bodies are and where they're raising their young. So not only does nature's chemistry and chemical processes not pollute, it actually creates conditions conducive to life in the surroundings. And so not only is nature's chemistry sustainable, it's also highly effective, creating very high-performing materials. So if we use nature's chemistry as a basis for how we can do chemistry, it doesn't mean that sustainable materials have to be less effective. They could actually be more effective and sustainable by learning from nature's ancient recipes. And so even though there's this really wide variety in the different kinds of characteristics that natural materials have, there are some basic fundamentals that are in common. The main one is that there's always 3D structure and multiple composition at the basis of it. So whether you're talking about natural molecules like DNA that we're all familiar with, it has a particular 3D structure and an order to its composition, from molecules up to macro scale stuff, nature uses 3D structure and composition to get those characteristics. And all of nature's materials are made from some combination of proteins, carbohydrates, and minerals, and depending on the material, maybe some waxes and stuff. But they're all composite materials. And this 3D structure is not just a big lump that's in a certain shape. From the molecular level all the way to the macro level, there's a specific hierarchical, ordered, layered structure. And so if you take something really hard like limpets are these little creatures that actually scrape rock to get their nutrients. So you can imagine how abrasive that is. And so the composition and 3D structure of its teeth are really these iron-based fibers. And researchers, there was just a paper that came out this year in 2015 that was saying that these mineral fibers are actually stronger than spider silk, which is already, said to be stronger than steel by certain measures. So even though these fibers are mostly mineral, there's also protein and carbohydrate in there to give it all of the functionality that it has. So then you move to something like leaves and stems and branches. It's also a pretty hard material, but it's got more flexibility, a little bit of permeability, and they're mostly carbohydrate. But there's also protein and minerals in there, and you can tell by, I wish there was a better cross-section of the 3D structure of leaves and plants, but you can see that there's this layered, ordered structure that gives that flexibility and the other characteristics. And then you have something that's really soft and squishy, like joint cartilage, with very lubricating, cushioning types of characteristics. And it's mostly protein, but there is also some degree of carbohydrates and minerals to give it its overall characteristics in a network type of 3D structure. So we're working towards being able to have a library that basically associates all of these different kinds of characteristics in natural materials with the 3D structure and the composition that gives you those, so that eventually we could say, okay, we need a man-made material that has, this suite of characteristics. So you would go to this library, see what kind of 3D structure, what kind of composition do you need to piece them together to get that combination of characteristics, but using proteins and carbohydrates and minerals so that you can then easily recycle. Not only easily recycle, but the manufacture and then disposal of these items, if they're made from the same thing that nature's materials are made of, makes it much more life-friendly. So we're really kind of entering the sweet spot. I mean, what's really interesting about Sam teaching young people is that, we're on the verge of entering this sweet spot where science is getting to the point where, we've got this biological research capability. So we have the tools and the analysis to be able to see nature at this molecular 3D structure to really figure out what's going on. We also have better dexterity with manufacturing things from the bottom-up layered sort of processing. So I'm sure you're all familiar with 3D printing, being able to print in layers. It's very crude right now. And I think that 3D printing is just the tip of the iceberg for what is called additive manufacturing. That there's going to be really great stuff that young people are going to be thinking of to take this information about nature's 3D structure and composition and actually be able to mimic it in manufacturing processes. And then the computer world of virtual reality and such, we're already using virtual reality to design cars and things like that. You can play with it on the computer, and it's not till you figure out you've got something that really works that you take it into the engineering lab and make something. But at the chemistry level, you can do sort of the same thing, and you'll be able to do that more and more. So we're coming into this sweet spot where the ability to make biomimetic materials is really a reality, not just a good story. So at 8 minutes and 49 seconds, I'll stop.
Mark, thank you. And it's interesting that in nature's chemistry also how the set of chemicals that nature works with is a much smaller set, and it's the most abundant of the chemicals we have around, and rather than our vast collection and we invent new ones, but that also that
Well, as I said before, I think that when I talk to young people about biomimicry, they just soak it up. And so it's really, you put that slide up about optimism, it fills me with optimism in a world where otherwise you just hear these doomsday stories that, there really is hope for the future.
I think the thing I would add to that, and we were just talking about this, Sam and I, there's an organization called the Biomimicry Educators Network, and over 3/4, maybe 4/5 of the people in that network are K-12 educators. Very few university, and I think a few of you here, I think there's some people from universities, and a lot of that's due to the work that Sam did at Biomimicry 3.8 in 6 years of very robust program to have materials and engage K-12 teachers who are very interested. But it's also rewarding to now benefit from all of those and see the numbers of K-12 educators that are working in this and are interested. So thanks to you for helping them. Go ahead.
Well, it's been something that a lot of people have been doing, and it's great to see it starting to take root. This conference that Peter helped organize for tomorrow, I was just amazed to see the number of teachers that are going to be doing these 1-hour workshops with other teachers, all on biomimicry. The chemistry side of things, I just wish I had paid more attention to chemistry in high school, because it wasn't until after I was 40 that I really started to get interested in chemistry, and started to see it the way that Mark described. And the idea that we've been pursuing is that it's really interesting to hear about biomimicry when you're a student, but it's even neater to actually do it and try it out. So that lab that Mark mentioned, and I showed you the photo, we wanted to give students a way to actually try out biomimicry themselves, whether it's in a chemistry, the topic is chemistry or engineering or what have you. We want to give them a flavor of what it's like to do this, to learn from the natural world and apply it to the things that humans want to do, because that's the whole point of it. The other thing I just wanted to mention is that this is a really interesting diagram, and Mark's way of looking at it I think is really interesting. I was thinking as I looked at it that I imagined a fourth circle, which I guess would be sort of about motivation. We have this growing capability, as Mark pointed out, with information, with the ability to manufacture and then test out these things. But we really need to instill in adults and young people the desire to make a world that works as well as the natural world, so that we're stopping on digging this endless hole that we've been digging for the last 300 years, and where is it going to lead? I think that what I like about biomimicry is it kind of gives us a vision of where we can head.
On this issue of green chemistry and biomimicry, I would just say for Biomimicry New England, that's essential. The two are part of biomimicry, an essential part of biomimicry is green chemistry. And we are going to do a course for university students, actually at UMass Amherst, 11 to 16 May, and it's biomimicry and green chemistry for sustainability. And John Warner of the Warner Babcock Institute and Amy Cannon of Beyond Benign are both going to participate as faculty, as well as several other people in biomimicry. So I think it's really important, and we're going to do as much as we can for moving that forward. Anything else you want to comment on, or should we open it up to?
I think we should
open it up. Questions. Now, the rule is you can't, unless you ask questions, you can't leave. So yes, please.
Sure. So the question was, are there lesson plans that are available for teachers to use? The answer is yes. It's limited to some degree, but there's some pretty great stuff out there already on the internet. There's the Biomimicry Educators Network. If you Google that, you'll find a whole network of other educators that are interested in biomimicry, and also some curriculum that exists already on the internet. And there's going to be more in the next year. There's going to be a whole bunch more.
Yeah.
This is sort of two related questions, and the first has to do with, I guess, K through 12 education and transitioning to university. And I'm coming from social sciences, and I know I wanted to be an English major, and I love hearing about this stuff. What I can't stand is the process of doing it. And I have never met a major in college who is pursuing a hard science or a math or a physics major that comes back and said, oh, I loved my OChem, or I love taking these courses. It's like 4 years of incredible stress and slogging to maybe get into someone's lab who is maybe doing something you're interested in. So I feel like these are great workshops you're doing, but seems like there's this huge disconnect between what actual professional engineering and STEM careers are and what you're having them do in this workshop.
Well, I guess, yeah, I would say, it is a long road, but these things are changing. Like I said, in the last 10 years, the number of biomimicry-focused courses or departments, whole degrees that you can get at colleges and universities, it's sort of exploded. It's going to grow even more, but it's changed a lot in just a few years. So I think that
The pedagogy
pedagogy
change?
That varies, of
Because I was
course.
told if you cannot teach yourself this stuff, do not take it at university.
Well, I think that varies by the educational institution and by the teacher. So, you have good and you have bad and you have everything in between. But my point is just that if you are a young person that is interested in this, there's a lot more opportunity to hope that you're going to get to where you want to go than there was even just 10 years ago.
And I think the other thing is that it's engaging. I mean, the statistics about women being interested, it's huge. And once you're engaged, it's amazing how much, if you're really engaged and you want to move forward, and this is keeping you engaged, you can go a lot further than, and in more and more places you can, create a path for yourself. So I think it's definitely changing.
Mark, you must. Mark is the living proof.
Well, to tell you the truth, though, the last thing I thought I'd ever be was a chemistry major, because I thought, chemistry, what does that have to do with life? And I took a year off between my sophomore and junior year and happened to get a job washing glassware in this chemistry lab that was part of an environmental consulting firm. And long story short, I ended up doing other things there, but really began to see an application for chemistry, that it wasn't just this esoteric thing. And I think now, if you can start teaching chemistry by giving examples of chemistry in nature, that would just really, spur people to want to continue with it.
Yeah, and I also think participating, John Warner tells a great story. I mean, John Warner wanted to be a musician, had his own band, and he happened to go to just by total accident, invited himself to go on a tour of a chemistry lab, and it changed his life. I mean, he just decided, oh, this is what I want to do. But it was seeing the opportunity to engage and participate in this subject, which he had no idea was possible. And so anyway, the question was, where is biomimicry being used locally? And that's, thank you, good question. And the short answer is everywhere, a lot of places. And the interesting thing is it's not called biomimicry, it's called bioinspiration. There are numerous labs at MIT that are doing amazing work, following nature's example and everything from trying to deconstruct spider silk to many other things. The Wyss Institute is just an amazing local resource that is doing incredible work.
Can you spell that? Wyss?
Yeah, it's WYSS, and it's pronounced Wyss. That's a name of a Swiss engineer who gave Harvard $120 million, and then a year and a half later gave him the second $120 million, and they're doing quite well, thank you. But it's a good question also because that's a focus area for Biomimicry New England. What we want to do is, because we're Biomimicry New England, is look at natural examples that you saw, but from New England, and document them. And we have a newsletter that we're going to bring out very shortly that will always have an example of a natural example, and it has one, and then also an innovation example that's local. And we'll have both of those in this newsletter, which initially will come out quarterly. But it's something that we feel is really important, what's going on in New England. But other questions? Yes?
And I guess I was hoping you guys could talk a little bit about concern that I've had about biomimicry in general. So biomimicry is an interesting field in that it's a culmination of engineering and biology. And as you were saying, it's a really great tool for introducing new people to concepts in biology. And just listening to a lot of the terminology that you guys were using, for example, like that nature is a library of all of these different solutions. I was hoping you could comment a little bit about the pitfalls of that, being that you can sort of misunderstand fundamentals of biology in the sense that, so the idea is that evolution isn't necessarily it's not a single direction path, right? It's the result of lots of random things that have happened, and it's sort of a culmination on one specific thing that is not necessarily the best solution. But I think biomimicry, there's a danger that you sort of push people into thinking that evolution is a very one-directional path.
Go ahead.
You know, the thing is that nature has been at this for 3.8 billion years and working within the context that we have. And we're working within modern industry is working within the context that we have at a much speeded up time frame. So, nature has had an opportunity to fail. A lot of the failures no longer exist because they failed. And it doesn't mean that the natural technologies that are around now are the most perfect things that could possibly exist. But they are at this point, relative to what we might be able to come up with in our mind, are, time tested, they're very highly efficient, and most important, in sync with the ecosystem, which is something that our industry is really far away from. Because if you think of our, modern industry just being 300 years old or so, and only having evolution industry is also evolving. But we're at the very beginning, whereas nature has been at this for a long time. And I certainly don't think that, you should never assume that just because you're taking a material or something from nature that you should just assume that, it's going to be safe and all that, especially when you're taking it out of its context. And any biomimetic material, any biomimetic product should be subject to the same, testing that any other product is subject to. So I think that's maybe one thing to be aware of.
So I suppose, I think you misunderstood my point, which was not so much, I totally agree with you that biology has converged on very interesting solutions that probably would not have come up either. Anyway, the question that I had more was, how do you present biomimicry to people who don't have a lot of exposure to biology and science, and prevent them from coming into like mental, or like thinking about things in a way that biology is that it's like a one-way path that you always end up, or that, I don't know how to explain this in a good way.
Yeah, I think that whether it's biomimicry or in the past, people have also looked at organisms as sort of these perfect things. There's been long history of religious interpretation of the natural world in that way that has also misled people to misunderstand nature. So you could have that same problem. I think the way you have to deal with that is educating people about how biology works, how evolution and natural selection have worked, how it's a work in progress, and it's a work that's constantly in relation to the environment. So I don't think that the problem that you're talking about, if I understand you, is unique to biomimicry, but so I think it's just an issue. Whenever you're talking about anything about biology, you might have that kind of misunderstanding.
Yeah, so the question was basically, we've been talking about biomimicry used to make things that, have a net positive effect, but could biomimicry be applied to making things that are destructive, for making more effective weapons or whatever? And the answer is certainly yes. It could be. At Biomimicry 3.8, we make a conscious decision that when we take on clients, we wouldn't take on a client that's looking to make a better weapon. It doesn't mean that other people aren't, and I'm sure other people are. The U.S. military is certainly seeing the value of biomimicry, at least in terms of putting money into doing research. I don't know exactly what's going on. It may not necessarily be weaponry, but like any technology, you can't control. Once it's out there in the world, you can't control. I mean, look, the petrochemical industry, besides from inadvertently poisoning us, was certainly used to make poisons to use as weapons. So that's where human frailty comes in.
It's interesting. There's a book called Learning from the Octopus by Rafe Sagrin, and basically he applies biomimicry to basically dealing with terrorism. And so it's sort of the opposite side, but it's a very interesting book, and to really a way to think differently, to back up and say, okay, a totally new frame of reference and a new way of approaching a problem. And I would say all of the examples that we've come across is really, and even defense-related research is more to do with the ones we know of is to do with propulsion and, energy saving and that kind of thing. And you do see that, and DoD spending money on energy saving and things like that, and alternate forms of energy. Other questions? Yes.
Yeah, so I'm kind of curious about how sort of teaching biomimicry and how working with different clients, if they see biomimicry as a way of talking about conservation, if it's more than just, we can learn things from nature, but we also need to protect them. If you guys have experience in working with different clients that maybe have learned these things, or or having conversations in like workshops with students, if there's more of a conservation ethic that comes out of those things, or if you have maybe some polls that you've read that have sort of said the same thing.
Well, in terms of working with clients, biomimicry is another form of innovation. And what motivates clients to spend money on doing motivation is varied. It could be because they've tried everything else and nothing else works, and they want to open up the solution space to solve their problem. It could be because a law is coming and it makes it impossible or difficult to do what they've been doing. They need to get rid of a chemical or something. So it varies. I mean, there are some clients that do want to be more sustainable. I think very often even that is because what it then looks like, publicly. But I think at the same time, even if they hadn't thought of sustainability at all in terms of biomimicry, once they start getting involved, I think they begin to realize that nature is really something we can preserve, because if looking at nature found new solutions that they never would have found otherwise helped them, then it makes sense to preserve the world, because if we get rid of habitats and the organisms that live there, we may lose opportunities to solve problems in the future.
No, it's a good point, and many more companies are interested in innovation than are in sustainability. And so, it's really how I got involved initially was shifting from design to, I felt I was really interested in sustainability. And the way to achieve that, I think you've got to harness the self-interest of business. And it's much easier to harness the self-interest of business around innovation. There's a statistic, it's a few years old now, that something like over 80% of the C-suite, the senior executives, are, not only do they all want innovation, but over 80% are unhappy with their investment in innovation. So, okay, they want it and they're unhappy with their investment. Boy, do we have a deal for you. We've got this R&D lab that's been in business for 3.8 billion years, and does she have some amazing solutions? And again, it's not, it's really looking at this library of opportunity. And then the great thing is, okay, the additional payoff is that it is sustainable. Because if you follow nature's rule book, it's inherently sustainable, period. If you're going to really go that path, it is. So, okay, let them focus on innovation. If you really use biomimicry, we all win. Are there questions? Yes?
Mark, could you, if you maybe quickly share a little case study or something from Biomimicry 3.8 some interesting project that you loved? Like, who was the client? What was their problem? Like, what was the solution?
Well, you're stepping on non-disclosure agreements there. But there is one that I can share because we partnered with UC Berkeley in trying to solve a problem that Levi's has. And so Levi's is a good example of a company that's not a chemical company at all, but as I said in my presentation, to give materials a certain kind of characteristic that all boils down to chemistry. So what they were trying to do is get rid of formaldehyde and diisocyanates that are used to make permanent press cotton or water-resistant cotton. So we worked with Marty Mulvihill, who's a professor and head of the the Berkeley Center for Green Chemistry, with a class to look at, how could we go about this with biomimicry? And the way biomimicry works is that, a company or whoever will come to you with a challenge, you have to break that challenge down to a function. Because then once you break it down to a function, you can then, try to answer the question, how does nature, do that particular function? So in the case of permanent press and water-resistant cotton, the way you get permanent press cotton, cotton is all these fibers, and these fibers stick to each other, almost like the gecko works with many low energy bonds or very weak bonds. But if you have a lot of them, and nature does this all the time, which is very different from how our chemical industry works, which is making really strong bonds that are hard to break. Nature makes maximum use of many very weak bonds. So between cotton fibers, you have these things called hydrogen bonds, which easily break and reform, which is why you may have a pressed piece of cotton, but if it gets wet or heated or whatever, those bonds break and reform, and they reform to whatever position the material is in. So actually, every time you guys iron cotton, if anybody irons cotton anymore, you're actually doing chemistry, because you're breaking all of those hydrogen bonds. They're immediately reforming, but you're pressing it, and so they're reforming so that it's flat. So industry had been using formaldehyde to add to those hydrogen bonds, but creating these really strong bonds that, once you saturate the material in this formaldehyde-based solution and you press it, it just stays. Those are now many strong bonds, but formaldehyde is a toxic chemical, and the diisocyanates were used to adhere basically a Teflon coating to the cotton material. So the function in both those cases was cross-linking or binding. So we broke that problem down to a function, which is cross-linking or binding. Then we looked to nature to see what are all the different ways that nature cross-links and binds, and we looked at hundreds of different strategies, but came up or boiled it down to 12. Some that plants were using, some that mammals were using, some that reptiles were using, and looked at what sort of patterns were there across organisms, and the class anyway came up with about 6 different possible concepts of how you could achieve that cross-linking in cotton fabric without using formaldehyde. And so now it's slowly being used. But any kind of innovation process is something that takes like 10 years. So, even though this was just like 2 years ago, there's still a lot of work ahead.
There was another question. Yeah.
It seems like lots of the examples that I've seen of biomimicry have been in academic settings. And it seems like a lot of that is because it's very complex on a material science and chemistry level, like the gecko foot or spider silk being a primary example. We're improving our manufacturing processes to get nanostructures or to get really specialized materials that have a complex 3D hierarchy. The manufacturing process just isn't there yet. So how do you see biomimicry breaking into industry in a way that's not just from a design aspect, like from a chemical aspect or from a material science aspect, given that the manufacturing processes that we have are very inferior to what nature has?
Well, academia really serves a function, because you have to do all of that research and find out how nature is working and do a little bit of play in the lab. But there are companies like Warner Babcock Institute, 20 minutes outside of here, the Wyss Institute or MIT's lab, that there may be some academic overlap there, but there's also an intent on commercialization. So I don't know exactly what MIT and WES have in terms of labs, but whether they're using the same labs that the classes are using, or if there are separate ones, they're geared towards commercialization, and they've commercialized products. There's one really interesting one that just recently came out. But also in the course of us working with clients, we have some strategic partners, of which WBI, the Warner Babcock Institute, is one, but sort of beginning to bridge that gap. So working with clients and saying, we're coming up with this idea, and now have this strategic partner lab that can begin to actually develop it. And I think eventually I'd like to get to the point where I've done this enough, and other people have done it enough, where we can actually work with the lab at the company and work with them to be able to do this kind of thing themselves. So I think it's really moving forward.
And one of the things we want to do is, as I said, for Biomimicry New England, is bring you these transition stories, especially ones here in New England. And WES has a number of spin-offs that are now, they're smaller spin-offs, but there's a number that look really great, and follow those stories and then get them to you. So the question is, does biomimicry solely function on the structure or look at other aspects? And definitely not just structure. Structure is important, but yes, for other things.
There's a lot more. I mean, anything that happens in nature, whether it's structure or whether it's behavior, whether it's metabolism, whether it's the ecology between organisms, all of those things can be emulated in some technology or design. And so one of my favorite examples, for example, is a architecture glass company. And they were confronting the fact that birds collide into architectural glass, into skyscrapers all the time. And they looked at how spiders create their webs and how birds don't seem to run into spider webs very frequently. And they found out that the spider webs they reflect ultraviolet light, and birds can see that very well. And then they put ultraviolet light reflecting elements into their architectural glass, and now the birds can see that glass very well, and it's reduced bird collisions into those skyscrapers by about 75%. And so, that's an example of sort of the behavior of what's going on with the material between spiders and birds that they were able to mimic. And there's lots of organizations looking at how ecosystems function and thinking about, well, maybe we need to change how we do our communication internally or how we work with other companies outside of us. So they're also looking to the natural world, but a different aspect than just, structure, material structure.
Yeah, and there's also many examples of looking at everything from swarm behavior and then the communication that happens to achieve swarm behavior, or how organisms collectively do things. So there's, biomimicry are there examples of biomimicry being used to help the environment? And I'd say the short answer is, as we said, all of them because of the approach you're taking, but specific examples.
Well, the last example I just gave you is literally saving millions of birds' lives every year. Very frequently, the technologies there's a cement technology, for example, that instead of giving off 6% of the annual greenhouse gas emissions when we make our cement the way we do, when we look at how coral reefs do it, it's actually removing the greenhouse gases from the atmosphere and producing the same material. So, yeah, a lot of the examples are good for the environment. Mark, I'm sure you have plenty others.
Well, one other example is this technology that was designed using kind of the processes that bacteria use to take metals out of water. So it was this contraption that was designed to be put into surface waters to basically mine the dissolved metals, mostly metals that are there because of pollutant effluents that have gone in there. So rather than having to mine land fresh for metals, you could actually be taking them out of the water and using them.
And cleaning the water in the process.
First, thank you, Mark. Sam, thank you both very much. So please join me in thanking both of our
panelists. Based on how long the tissue turnover rate is, or basically what period of time a manta biopsy represents, we now know that these guys are staying put or at least aren't mixing with other populations on multi-year timescales.